Wait, okay. I'm gonna wait like 3 minutes, but I'm gonna assume that we're not having so I will start. Um,
Welcome, Yajin. No, I saw the email. I was like, oh, wait. Oh, Yajin. Just see that. Like, nothing's coming out. It's intentional. It's exploded. I know. I'm like, get out. Yeah, that's just saying, like, the next day, I get the I heard it really good. Yeah, like, yeah, they can. I did this go. I did.
Yeah, I mean, obvious.
I know somebody. I know somebody. Yeah, I do like. It's very temporary. It's not like it's just.
She's measuring about.
I want to do mine. Yeah, to get. Zero times two.
so today's class is like the history of different things. There's like, I don't know, like maybe 1,000 slides, so I'll never get through it all. But next class I'm starting something different. Next class we're gonna start with foundational stuff. And so I would like people to bring their computers so that we can follow along. I think I'm going to try to devote several classes to the grasshopper stuff and the patient factoring behind it. Some very few people have that in spades, but people that don't have it, I'd like to try to slow down enough that you can actually get it, since it takes a little bit of time to start. In terms of the there's this other video up in this slide presentation that's a recap of the principal curvature thing, and then there is how to do the panelization, and then there's also the recording of this lecture online. Okay, so this one is about like the other side of all of the stuff that I was talking about with the models at the beginning of class. So back to this idea that some models are representational, and then that there are also, but this word model, I think, is a very important word in the world. It's a multifaceted word that means many different things. So these ORI models, they are sort of two versions of the word. They're both miniature representations, like our typical architectural models, but they are also a scientific idea, right? They're the model of a solar system. They're an abstraction of a context. And this second definition, I think, is actually the more typical and more precise. So a model is like an abstraction or a simplified version of reality. And looked at in this way, the models are always incomplete, and they're always partially accurate. And in giving up this pretense to totality, I think the model gains something important in return. It makes it projective as well as descriptive. So they help us predict the future and make decisions. That's what models really are. So this is also a model, the standard model of particle physics. A model is sort of a framework or a simplification of reality that helps you make prediction. A number of years ago, there was a log devoted entirely to models, and every single author put forth a different definition. I thought Eric's essay in there is very excellent. He explains all the many different kinds of models that were used in this project. There were 4 different models, and each one is used to verify another. So there's first the Rhino model, which is sort of defines the geometry. And there's a structural model, and then the fabrication model, and then the real building was also a model that was used to verify the structural calculations. So, and they also performed multiple kinds of structural calculations, hand calculations, physical simulations, digital simulations, in dialogue with each other. And they all yield different results. So this idea that the model is never completely accurate and that you need multiple models to verify one another What he says, models are approximations, whether they're physical maquettes, digital files, or simulations. And it's easy to overestimate the precision implied by the digital tools. It's very important to me. When you get like even something like a laser scan, it is first processed by the person that took it, and they give you a Revit model or something, and that is always inaccurate in some way. So there's always this discrepancy. So he also says a model is a useful fiction, an imperfect approximation of reality, just useful enough at times to serve as a means to predict conditions and act on the physical and material world. I think this idea of the model as an abstraction, as an approximation, as a tool, rather than a representation, very important in today's world. Mark Lee's essay talks about how the model is tied to iteration. It's always in reference to a larger set, of which it's an example. And this relates to the notion in our class that each model is a model for the next model. And, you know, a prototype or a mock-up rather than the final version. And so each model includes its own failure and also its own future ambitions. So, you know, in architecture, we also always have to do actual mock-ups, prototypes of the systems that come together. There's this wonderful book, Archetype, that photographs many of them at night so that you don't see the context. It's just interesting because if you don't, even though you predict all the details with the digital tool, when you build it, there's always some excess, something left out that needs to be refactored into the idea. And so it's essential to do that. We blast them with rainwater, we blast them with sand, we hit them with all sorts of things. It's a never-ending process of testing. So these are all different definitions of a model: a miniature, a prototype, a mathematical description, a computer simulation. The process behind the simulation, you know, the sky model or the material model that's being used. An AI is a language model or an epistemological framework. And what I want to talk about is this other version of a model, the model in science, which is a mental or visual way of linking theory with experiment. The model really as an experiment. That's what I feel is interesting. The model as something that you test an idea and you learn something from. I think, you know, I love this. This is a climate model, right? They're always very inaccurate, but they attempt to predict the future, and they include in them the acknowledgement of their inaccuracy. So they give you a range of what their prediction accuracy is. And I think that idea of enfolding into itself its own bounds is one of the most beautiful ideas in science that is important to always remember. So back to Eric's idea of validation, you know, a validated model, he calls it verification, but in simulations called validation, the idea of comparing the outputs from your simulation to other things, either other models or to reality. And so the difference between like a rendering engine that we use to make representation and the rendering engine Radiance, which is used in Climate Studio and the other environmental simulation software that you use, is that these are validated, meaning that they have been compared to HDRI photographs and to other models, and they include within them the acknowledgement of their own limitations and their degree of accuracy, which is a completely different idea and amazing. And then there are also zillions of models sort of embedded in this. So, you know, there are many, when you do a sun irradiance map, there are sky models that are being used, and there are different ones. You know, they're not all the same. There's the cloudy one, the Perez, there's different ones. And so this acknowledgement that when you hit the button in the black box, there is a validated model, and that choosing the model is not exactly innocuous. I think that's a very important thing to remember in this age of AI. You know, this is what a sky model looks like. And then there's also, you know, occupancy models that are based on real studies. You know, when you load the occupancy, it's based on, you know, different studies that people have done in real scenarios. And this idea that, you know, when you do such a study, you report on who the study was done and where it was done and what group of people it was done on and how many people it was done on. So this idea that, you know, a real model, a model as an experiment, a model in this more expanded definition always acknowledges its own limitations. And so I want to talk about this idea of the model as an experiment in the sense of what we're doing in this class, which is physical experiments with materials and the history of that. And then if there's time, I'll talk about the environmental side of that as well, which I'm also interested in. So I don't know if Iman spent time on Gaspard Monge, but projective geometry and Monge used to be the starting point of that whole class. You know, he was a French mathematician in the 19th century, end of the 18th century, and the founder of descriptive geometry. And these sort of drawings, they're often talked about as though they represent an increasing abstraction from the process of stone cutting, the process of moving those set of ideas outside of the realm of the craftsman and tradesperson and into the realm of the architect. But also, I think implicit in those techniques is this idea of projection as something that is tied to vision, and vision being tied to light, and light, because it travels in straight lines, being tied to uh, linear surfaces, conic surfaces, and ruled surfaces. And so there's an alternate history also beginning with Monge that really is about the origin of studying the ruled surface. And I think these set of images explain sort of why that's connected. This person, Theodore Olivier, was Monge's student, and Monge made some models, but he also started making many of them. And these string models were built at the same time that projective geometry and descriptive geometry were being founded. And there were hundreds and hundreds and hundreds of them built, and they were sold all around the world to various universities, and they became the instruments for the exchanging of mathematical knowledge and the sort of popularization of these concepts of, hope this plays, these concepts of the ruled surface. There's a very beautiful video, which is included in here, which is not playing, that shows somebody playing with these models. They are all weighted with weights that go into the base, and little hanging weights, and they move. So you can explore the transformations of these geometric models. So there was a whole industry that grew up in the 19th century of making all these models, selling them to museums around the world. And originally, many of them were made by this man, Olivier Monge's students. But also many others were made. And there are many collections with these things all around the world. Harvard has some. Here you can see the weights hanging from the model. And they were of all kinds. So some of them were very high end, and some of them were very low end, like this collection of little descriptive geometry postulates, which was like the CD-ROM or the little online thing that would get with a textbook. Okay, so these are the ones in Harvard's collection. So I think the dissemination around this time, this is in 1908. Gaudi was using these started using these ruled surface forms in his work. And I don't know how documented the connection between those is, but certainly there was the same time period, and the ruled surface, the hyperboloid and the conoid appears in his work. And so I think the dissemination of those mathematical models at that time was inspirational there. There's this whole history also people always bring up of the hanging chain model. The first one was that I know of was by this guy Heinrich Hubisch. He was did these churches but he only made two-dimensional ones. So they were often advocated for in structural analysis textbooks as a way to, after the fact, sort of follow the load paths in your model. But they were these 2D after the fact analytical things. And then the first person I think who made a 3D one was for this incomplete competition, this man Fritz Gosling, and he only made a little sketch of it. And then of course there's the great one, suddenly the Gaudi one, And this one is a 1 to 10 scale, 4 meters high and 6 meters long. It was built next to the hut of the Conel Güell church. It's not for the Sagrada Familia, it's for the Conel Güell, which he himself called a model for the Sagrada Familia. And according to Rainer Graf, who writes a lot about this and studied them, nobody really knows where he got this idea. He thought he was the first person to do it, and it's not clear where he got the idea to do it at such a fundamentally large scale. But basically, he would move these weights around and use the weights to refine the form. And over time, the form would take on its shape, and the weights would be refined. And then they would measure it for the actual building. And there were no construction drawings. Apparently, he would just take pictures of the model and draw over them in order to describe the perspectives of the building. Like this. But I have to say, I feel like he probably got this idea. It's not documented, but I think he must have gotten it from these, which are also these hanging three-dimensional forms that were the same place that he would have gotten the ruled surface thing. And you can see the same forms here in the Museum of the Sagrada Familia. So these are the mathematical models, the Olivia model, and this is one in the Gaudi Museum. Okay, so these models actually they disseminate, and the model disseminates and has a huge impact on a lot of people. Particularly, I have a slight detour here before I return to hanging chain models. There's this mathematician I very much like, Dinah Tamina, who's the person who depicts a lot of hyperbolic space. And she is the one that took these photographs of the Gaudi models that I'm showing you right now. I found them on her website. She used to work with William Thurston, who is my favorite mathematician, very kind man. He writes about what it's like to be inside of sort of distorted spaces. This was his model, and she does these crochet models, which are the way that we have learned to visualize curved space. And those are very much related to the Escher drawings. This is another representation of curved space. It's supposed to be a universe that is fundamentally curved, and so your scale changes in relation into this projection. And she found this other way of doing it with these physical models. The idea of crochet is that every time you add a stitch, the stitch is either square, it either repeats the world at the same scale, or you can do an increased stitch or a decreased stitch. If you do an increased stitch, it's like the world fundamentally expands. The world kind of gets bigger. And so you can make these worlds where the space of the world is growing or shrinking, and it results in these implicitly curved surfaces. And before her, the only way we used to visualize that was with these sort of Escherian representations. So somehow the physical model, the legacy of one great physical modeler, influencing another. And there are many examples of this in art. This is Alba Albach. Also the same principle that if you add an increased or a decreased stitch, the world starts to curl up on itself. And also the same thing with Ruth Ozawa. Here, there's an idea that somehow the physical material process is often essential for our intuition of understanding something that is otherwise abstract. Interestingly, the first person that made a model like that was this man, Eugene Beltrami, an Italian mathematician, and he also influenced this artist who is also obsessed with Gaudi. All right, so I want to go back to the hanging chains briefly. This model, the one we usually see, is not the original. The original was actually destroyed. This is a 1 to 15 replica of it, and it is the original was 1 to 10. And so this reconstruction was carried out by that man, Rainer Graf, I was talking about, and also by Frey Otto's students in Stuttgart at the Institute for Lightweight Structures. So there's a connection between Frey Otto's sort of interest in these hanging chain models and the origin in the Gaudi. So they did actually scans of the photographs of the originals, comparing them to each other, and then attempted to reconstruct a digital model from it, and then to rebuild the hanging chain model from that. So there's a interesting. Also, they made a balloon one. So I think these models that we actually see when we go to Barcelona are not the originals. They are ones made by Frey Otto students in the 1980s. And then also Frey Otto around the same time. This is competition a few years later than the making of the previous model. Did his own hanging chain models for his own designs. This was for a project in Saudi Arabia. He did not start after the Gaudi model, started much earlier, making many of these hanging chain models in order to try to visualize the structural forces in the grid shells that I talked about in the first class. So there's this incredible book, Thinking by Modeling, that shows many of his sort of physical model examples that try to address these ideas. And that is, this is also another hanging chain model that led to this multi-hull, Mannheim multi-hull project that I referred to in the original class. So there's a direct connection between the study of the active bending surfaces, the physical modeling legacy of Gaudi, and the physical modeling legacy of Frey Otto. One thing that Frey Otto is also famous for, these soap bubble models. So these, he's not the first person to do that. They were, I think Joseph Plateau was the first person in 1844, realized that when any single loop nature would find a way for the soap bubble to cling to it, and try to start to format that into a set of laws, which led to our understanding of minimal surfaces. The same people that used to make the hanging chain models, one of them was this company Schilling. This guy Alexander Brill also made these. So it has its origin in the same time period, in this fascination with the three-dimensional world, in its physical structure and what that meant mathematically at the start of the 19th century. Frey Otto made many of them. What's interesting about Frey Otto is he's often sort of classified as this kind of engineering figure in architecture, but it's not actually the way he thought of himself. He was fascinated by things like this, by spider webs, or what he called incalculable forms. There's a person I admire, Daniela Fabricas, who writes a lot about him, and she talks about this idea of a form that is at the sort of sublime edge of understanding, something that can barely be measured, can barely be grasped. It's too light and or too small, or too thin, or too hidden to possibly be measured and understood. And so he was interested in sort of this strange, almost sublime exploration at the edge of the discipline, actually, rather than in engineering. He was very distrustful of many of the sort of engineering methods, and very annoying to the engineering department at Stuttgart. So actually, it's a different sort of playful, odd, experimental legacy that comes out of that. That also then has repercussions for engineering. Eventually, gets folded back into it, which I think is interesting. This sort of tension between the playful, open-ended thought and the more systematized discipline. So he made tons of these, tons of photographs of all these soap bubbles. They're very beautiful, but they had no way of doing anything with them. So they actually began to do all of these experiments to attempt to preserve them. They controlled their chemical composition. They put them on stationary things that were anchored into the ground inside of airtight chambers, and they got to the point where they could preserve them for, weeks at a time without them popping. And then they developed this whole method of photographing them. They would rotate them and take photographs from different sides and invested in the study of photogrammetry, which is the study of how do you capture a three-dimensional object in still photos. They would do these rotational things, and they would also do these projections. They would project grids onto the models. The model was in a chamber that had this light shining down on it, so it was already in a gridded space. They would photograph it in all of these particular ways in order to try to capture and describe what the space is. So the model is incredibly ephemeral, but the apparatus for photographing it became this wild machinery. This was the final one in 1973, the machine for photographing soap bubbles. It has like a camera, and it has an airtight chamber, and it's drilled into the floor, and it's chemically composed, and you can rotate the model in there. And this is how they would photograph them. So they would follow a process like this, where they would have this soap bubble model in a gridded universe, sort of like Daniela says, sort of like the interior of a computer. You can't reach it. It's separated. And then once they measured it, they would build a second set of experimental models. They would be these fixed models that would no longer be movable, would no longer be changeable. And then those models would be subjected to different forms of measurement. So this huge apparatus to try to measure the unmeasurable. Yes.
Get to the point of like creating a massive machine for bulk model exploration. Like, and almost like how much that machine cost, or like what the profession was that made that valuable enough to explore. Like, sometimes I think like that for us when we get to make like models, and it's like arts and crafts almost, but there's like obviously value to a building that we can eventually get paid for. But
Yeah, I mean, I actually think maybe the world is I think this is a really important question. I think maybe the world is slightly more flexible than that. Like there are avenues for these things, and I think it's very important actually as when you're young people, you're young enough to access all kinds of them. Like, this school has funding for like young faculty that you can just apply for. You can get small grants for things like that. There's also all kinds of prizes and awards. There's also all kinds of fellowships. There's different kinds of grants for all sorts of things. And so actually, I actually think there's a huge world of like small grants that you can get to fund various sort of odd ideas that you have as a starting point. And then there's larger ones as well. And so I think actually, the people that are most successful in doing these kinds of things are people that apply for those things a lot. So I actually think it's a really important thing. I mean, you're before that now, and it's actually if you start thinking about it now, it's really open to you when you graduate. There's different traveling fellowships, different artist residencies. When you get to my age, it's a little more challenging because like you're stuck in a spot with people that you depend on you and things like that. But when you're young, you can travel about and you can apply to things. And, like I think, if you believe you're not going to get those things, you don't apply to them. But if you apply to enough of them, like I have a lot of friends that have won various awards for whatever. And so I think, I don't know how he got the funding for this. He was at a university. So when you're a professor, there's funding available. So like you get a certain amount of research fund, and then also you're in contact with other people that you can, ask about things like that. So like, I don't know, like when my friends and I, when we start a project, we immediately start looking for funding sources. So like, and then also I think you can do some research in connection with a project sometimes, like typically, there can be a little excess sometimes in an actual project to do some of that. So it's a great question. I think all of that was academically funded. That would be my guess. But some of it might have been funded for the buildings that he was building as well. So I'm not sure. I could look into that for you, but I don't know the answer. But I think it is more available than you think. So, then they would do these tiny um, still models, and they would weight them, and they would photograph them as they changed in order to try. So they would hang weights on them, photograph them twice, and get these overlapping time lapse images to see the actual loading under loading conditions. Okay, so in order to measure this, there was a giant measuring table that it would sit on. Um, and they would, hang plumb lines to figure out where things were. And it was set up, they would get these images like this, where they would time lapse, overlapping, double exposed images showing the movement of particular nodes that were numbered in order to try to figure out um, the loading conditions. And because the models would deteriorate over time, they were photographed simultaneously with innumerable cameras like this. By the way, I think one thing that's interesting is actually they were not very accurate. They spent all this time attempting to do all of this accuracy, and actually they weren't. I think in the end they were computer engineered. It was happening at the same time. This was happening at the same time as the birth of computer engineering. Part of the other reason why it might have been available to do this at the time is because there was a huge industry of measuring models, which at the time. But still, I still think that there has to be a process of testing and a process of failure in order to do anything like original and in order to do anything new. I guess what I'm advocating for is like the extreme willingness to try something that may not work is what I really believe in. I think there's no way to learn anything without accepting the possibility that your model might just collapse and fall apart. But there was a whole industry, like there was this, you know, these micrometers that would, measure the tension in a wire because people did this a lot at the time. But still, even though they didn't use it, it is true that the soap bubble translated into the um, physical model, then translated into a mold, then translated into a an actual building, which is this is the zoo in Munich, which I just think is I don't even know. What? You've been there?
No, I'm going to.
Oh, very cool. I think so. Even though they didn't end up using the engineering models, the discipline to do it did generate something very unusual. Okay, so then there's the age of, by the way, I really appreciate your question. I have to say, like, maybe next time I give this lecture, I'll do a part on funding sources.
Okay, well,
There was like I was saying, an entire industry at the time about physical model testing made possible by these, which are strain gauges. They were developed in the aircraft industry. And basically, it's a little tiny capacitor. And when you put it on a material, if the material stretches or bends, it bends too. And that changes the electrical current. And so you can tell how much force, how distorted something is. There are all these devices at the time or these things that would be it would project a little dot and it would see if the distance changed, and they would cover models. This is a model, Heinz-Heisendorf model, covered in the strain gauges and subjected to loading conditions. And then there are other ones, that would have 2 points drilled into a material, and then you would then you would subject the material to load, and you would put the 2 points in again, and it would be able to tell if it had moved like a micrometer. And then also the deflection gauges, which are like, they measure whether something has gone up or down in reference to a reference point. So, all of this was driven by the aircraft industry, okay, by planes and boats. So there's a huge issue, which I think is one of the most beautiful areas of scientific inquiry, which is this question of whether or not you can scale something up from a tiny model into the real world. It is intuitive but wrong that things scale. Nothing, a little thing does not scale to something big in most cases. Galileo is the first person that thought about this. He said, I've always regarded as false, though current opinion, that in speaking of these and other things, one cannot argue from the small to the large. And the first person that sort of made headway in this problem was this this guy William Freud. Okay, so there's this idea, the way that you can scale up from a tiny model of like a boat, little boat in water, to a big boat is through something called a dimensionless number, what's called a similarity parameter or a dimensionless number. Basically, it's a ratio of different quantities, like the speed divided by gravity times the height of the boat, that happens to hold true at the large scale and the little scale. And people experimentally have found out ratios between quantities that are true in both scenarios. So like the speed of the boat divided by gravity, by the square root of gravity times the height of the flow is true for a little model and a big model. If you get it, if you set that ratio at a large scale and you set it at a small, that you duplicate the same ratio at a small scale, you can take certain measurements that are comparable. So there are many of these. William Freud in the 1800s used to drag boats, drag little things through tunnels, through water to try to find these parameters. And they, over time, through experiment, people have found these quantities, the dimensionless numbers, which these ratios where the units cancel out, that through experimental verification hold true across scale. So the one for wind, which is the one I'm most familiar with, the Reynolds number, it's the size of the model times the speed, essentially is a parameter that you can set, you can measure certain characteristics. So basically, this idea of the density times the length scale, which is like, it's like if I wanted to measure a giant boat and I have a model this big, this would be the length scale of the little model, and the boat would be its true length, times the speed. And those things give you characteristics of the flow. So, like a large ship has a certain Reynolds number, and a small fish has a certain Reynolds number, and a swimmer has a certain Reynolds number. And if you want to make a model that gives you a certain that matches the flow characteristics of a big thing, you have to match the Reynolds number or one of the other similarity parameters. So this is the way it works, and this was developed in the wind tunnel testing industry in before and after the war. And so those ideas migrated into the building industry and allowed for people to do physical model testing in a precise way. They used to build these enormous wind tunnels. But actually, we still do use these because it is not, our simulation software is actually validated in the wind tunnels rather than the other way around. So that is how we know whether the simulation is correct by comparing it to a wind tunnel. I have done wind tunnel testing on my own building, so it's something very, very current now. So at this time, though, there was this huge industry in the 50s and the 60s. It's kind of like the golden age of physical model testing, where they would test tons and tons of engineering models. So, and there were many, many labs around the world and many different important figures. One of them is this person, Edward Torroja. He's a Spanish engineer. And he's one of the early people doing this. He was building these vaults and domes. And it was impossible to carry out the analysis of these structures analytically. And so he would, they would build models and they would weight them with all of these gauges on them and see whether they are distorted. And also he would build, this was for another one of his buildings, they built this models like this that were pulled on from all different directions, distorted with all different kinds of loading forces in order to see whether they would break. And actually, they would find out, certain things would collapse. They would test them to failure and then redesign them. Uh, and then there was in Italy a very significant lab, the Istituti Sperimentali Applicazioni di Calcestruzzo. I don't know how to say it, the Experimental Institute for Models and Structures. This is where Pier Luigi Nervi was. And they used to test dams here, giant physical models of dams, because this was university and public funding, and also for actual projects. So it was sort of combined university, government, and actual building projects, very tied to hydroelectric power. And so that's why it got going. But then many of the buildings that were built were tested here. This was in the 50s, 1950s. There were two kinds. They would do these full-scale models that they would load under various conditions and measure. And then they would also do full-scale components that they would stress and subject to failure. Okay, so I would say a lot of the information that we use for analysis still comes out originally of the physical tests. And then, so this is one of Nervi's buildings, St. Mary's Cathedral in San Francisco. There's the physical testing model to test the wind loading on the building. This is another one of Nervi's, an aircraft hangar covered in weights. That is this building. Okay. And then there are other people who, another character, even more experimental outside of just, engineering. This person, Heinz Eisler, is the person that created a lot of our theory about shells and domes. And he used to create these fabric form hanging models or build them in the earth and then turn them upside down and test them. So they're textiles saturated with resin that are then dried, and he had these frameworks so they could make them very quickly. And he has many vaults, many domes, these tennis shells around the world. His famous papers, New Shapes for Shells. These are some of them coming out of that research into fabric formwork. And then also they would also do them this way by blowing up bubbles and casting on top of them. So designing these little machines. I think this is out of order. I think that's one of the Taroja ones. Another person in Italy, this person Sergio Musmesci, did again similar to Frei Otto. He did soap bubble experiments and then tensile framework and then mock-ups in the same place as Pier Luigi Nervi in order to get things. This is a 1 to 5 mock-up or something like that. Okay, so there's this giant culture of physical model testing, and I think this culture is important because I think that it is. I think that there's a tendency to view knowledge in today's world as sort of encapsulated or hard to access. And I think that, I think when you come to the software or you come to a school like this, it feels like there's this, huge edifice of impenetrable information that you just have to try to absorb. But I think a lot of the discoveries and a lot of the things that are interesting are actually open-ended, and you can discover it yourself by just making a little tool and testing it yourself. And I think that a spirit to play and to trust yourself, even if you're not an expert in something, is what's important. I think you do not have to be an expert in order to take something on and test it and try it. I think the expertification of testing is very detrimental to people's sense of empowerment and sense of creativity. So then another person I very much admire is the person Ulrich Elias. I've talked about him before. He advocated for a certain playfulness, a kind of a juvenile amateurism uh, in design of structures, things in between, not categorized, not known. And he's considered the father of spatial structures, Plessy thing, but he was totally strange outside of the discipline, just making these things with the students at Penn for years and not being willing to necessarily looking in between for things that were not only structurally interesting, but also might change the way that we thought about building infrastructure. And he said, I think really the secret is to be curious. You see, we are our own first problem. What makes us different? Why should someone be interested in some stupid things like leaves, which are not stupid at all? But, we are very mysterious. People have got a personality, and maybe they're not interested in leaves. I like the idea that whatever you're interested in, whatever strikes your fancy, is a source of questioning and a source of experimentation that probably hasn't been opened by anybody. And I think almost as soon as you start studying anything, you become the expert in that thing. And to remember that when you go out into the world and you think that you're supposed to know everything already, maybe nobody knows it, and it's out there to be discovered and learned from. So he's the one that made these models, and this is this wonderful essay called "The Things Themselves Are Lying," about all of these sort of experimental structural models that really are caught in the realm between play, between playful amateur curiosity and something serious. And I think that is the place that I want us to be in. If your models don't come together, if they fail, but if you're curious about something, I think that is a necessary place to be in, and what I believe in. Then there's also Antig, who is another sort of playful experimenter driven by her personal passion about geometry and platonic solids, extremely personal, idiosyncratic research into these platonic forms. She worked with Conrad Reichman in New York for a while, the person that did these, and then is also the person responsible for like most of the geometric complexity in Kahn's work, like the ceiling at the Yale Art Gallery, and also for this wild tower which comes out of her TIG toy, and also these incredibly intense platonic solids. And this house, which I think is a lot like the project that you're doing right now. And also, I love this project. It's very obscure, but the idea of inhabiting a surface for personal passions into geometry, but then also negotiating that kind of personal curiosity with some very intimate human scaled things. So there was a great conference about her a number of years ago, which you can still watch. Then there's also in the spirit of play is this Black Mountain College, very famous school that was founded, liberal arts college founded in the 1950s and in the 1930s, sorry, that had a huge outsized legacy in modern art and modern architecture. They were there. Joseph and Annie Alpers were leaders there for a long period of time. It was all about education, this very kind of utopian community. Education is a lived experience, play, emphasis on process over product, experience over knowledge. And many crazy things came out of there, like the Fuller Domes, and like Ruth Azawa, and Erwin Hauer was another student of Joseph Alpers. Joseph Alpers, by the way, also wrote the book on color. This is unrelated to models, but he wrote the most famous book called The Interaction of Color. And the person that painted all the plates in The Interaction of Color is my mentor, Robert Reed, before Scott, who did all these wild paintings. So the greatest American art educator died a few years ago. Okay, so also then small models also playful. So I think the amateurism and the discovery, the playfulness relates very much to the engineering models. They're oddly tied together. Frey Otto, Ulrike Leis, Ian Ting in the play category, and Heinz Eisler and Edward Taroja and Pierre-Louis Julervi in the engineering category, but oddly very close together in outcomes in the discipline. Also, by the way, this sort of paper folding experiments, the fact that this paper folding was not done by Ron Resch. There's this great video of all of his paper folding, um, documented from 1992. The fact that paper folding cannot be very easily modeled in the computer, uh, is what led to the development of kangaroo. Okay? So Daniel Piker, when he was a student, was obsessed with Ron Resch and realized that it was impossible to model these paper structures in the computer. And so he developed kangaroo personally as a student, started as a student in order to make digital models of paper. Okay, so the physical impulse is also usually responsible in the end for the digital tool. So all of this ended, by the way, all the physical model experimentation ended in 1972 with the introduction of finite element analysis, which I'll talk about a little more in detail. But which is really breaking down something into little pieces and doing analyzing all the equations of structures billions of times. But initially, in the early transitional period, like for the Sydney Opera House, things were done both ways in physical model testing and digital simulation in order to validate each other. Okay, but I think now, we're in a very different time. I think we're in a time when the digital tools have advanced so much that they are actually able to take on again the physical. So we're back to the beginning again, which is that for a while we would use analytical equations to model physics, but now there's a lot of people that do the visual graphic statics again in the digital tools and then build things physically and validate them with each other. So there's no set of principles, measured. There's no easy way to analyze, a hanging chain. You need to do physical tests, do digital simulations, and build your own tools or build your own, library. So this is, where I think a lot of research is right now. It's back in this both and world. This is Sigrid Adrianson at Princeton doing stuff with dancers and hanging chains, very inspired by Frey Otto, and also doing stuff with active bending and bent plastic that is, the material is where its elastic properties are incorporated into its structure, which again is some of the stuff that we're playing with. Or Akim Menges in Stuttgart, his idea of measuring the properties of wood under deflection, or when it's wet, or when it's bent, or when it's cold, and then using those to build digital simulations of the tools. So the idea that the physical and the digital are brought together. And his idea is actually this one, that material is a form of computation, that the material actually computes the forces within it. And so there's a kind of a parallel self verification between one model and another. Another person is Sean Alquist. I talked about him before, who does at the Social Sensory Lab, doing tensile fabrics and the way those form shapes under tension. Another person is Jenny Sabin, who studies architecture and material science bioluminescence, and also tensile structures. Another person is Brandon Clifford and Wes McGee, who do, gravity center of mass studies and self things that are easy to assemble because of the distribution of their weight. Another person is, um, the all of these Gustavino vault studies that John Oxendorf did. Originally began, I think maybe 20 years ago because there were all these Gustavino thin tile vaulting structures that nobody really understood how they stood up structurally. We didn't have, I think, at the time, the tools to analyze them or really have the structural theory that understood how they were supported. And so he was doing his own physical tests, building things in his office, as well as developing tools with grad students to study and analyze these things that they found in the real world. Then one of his students, Philippe Bloch, is the person that kept going with that kind of most intensely. I think it's interesting, they tried at the end always to break the things that they make because surprising structural results that they didn't expect came out of that. And they published the software that goes along with these physical experiments, Rhino Vault, which is free to use, which allows for the analysis of graphic statics in 3 dimensions in Rhino. Graphic statics is what originally was a 2-dimensional art in the days of Gaudi. It's what he needed to use the hanging chain models to get out of, and it's what was abandoned when analytical computer software took over structural analysis, and it is what has come back today with the more sophisticated tools that we have in the computer. So the allowing of form finding in relationship to structural forces. But his work has a huge physical testing component. So they would design these sort of vaults in Rhino Vault, but also require a way of creating and getting the actual physical to match with the digital. And that was through this adjustable joint that they would position in space and then tweak individually and then measure the structure and run it again through the software to figure out where they needed to twist to tighten it to get it to match with the structural prediction. So whenever you're doing this type of advanced form finding, there's always this extremely analog process that needs to be engaged with in a very detail-oriented way. And then there's also the digital tool that supports it, and they're never the same. They never correspond, and they are all. And it's actually the negotiation between those two things that's the discipline of interest. Another person who does the graphic statics is Masood at Penn, who I very much admire. Built this glass bridge recently using the graphical method. Or another person, Nick Brucia. I've showed his models before. There's also Janet Eckelman, who does these tensile structures. This one was at the MIT Museum, was in a collaboration with their analysis associate professor there, Caitlin Mueller. So she developed digital tools that would learn from the artist tools and then would create a digital simulation of the physical, and the two of them in conjunction with each other allowed for the development of these type of a more complex form. Okay, then there's also Marc Crouvellier at Cornell, who does these sort of structural models, very, very, very precise replicas of buildings with students in order to study the structural principles. Finally, I think there's people that are not in the structural realm, that are just in the material realm. That has to do with just exploring the properties of the material independently, or the culture of making. This is Gabinette d'Architecture. They do, they're interested in brick, not because brick is a good structural material, but because it's it's what people know how to build with in their area. So they do all these tests to replicate the structural properties of various building components through brick. And then also Ensemble Studio, who they do things like this, where they, burn concrete, or they cast something and light it on fire, or they hack it to pieces, or they cut it in the ground, just to try to see how the casting process of the physical model is going to relate to the physical process that they will do at a large scale. And Holtrop as well, doing interesting things with physical models. Or Jay, who will join us today, is interested in monomaterials, in things that are made of basalt, only basalt, wall types that can be made with a single material, and building their own material prototypes for that. I also think, interestingly, there are people that return to the same things from history. This is the hanging chain model, but replicated by this artist, Aurelio Munoz, who does woven versions of them again. So the constant return to the same source material, I think, is also important. Okay, so then there are some there are some there's different environmental versions of this. So I think there's also a lot of physical testing with the environment. There's these originally these heliodons that were people still make them. Christoph at MIT has one, I think. There are two kinds. Either we have a dome that shines light on the model, or we can actually tilt the model to align with the light coming in. The greatest one of these is the thermoheliodon. I don't know if you guys have seen this before. Victor Olge and Aladar Olge at Princeton in the 1950s. They're the people that were obsessed with, solar shading and bioclimatic design. Wrote both of the books on those things, and they created this wild machine, which was supposed to I think it has fans inside that are supposed to simulate wind, and it has like earth inside that's supposed to simulate humidity, and it has, lamps inside and the sun overhead. It was supposed to be like a total environmental simulator of a building. I think they were never able to actually get it to work, but very inspiring, I think. I don't know if that jives with you guys. I find the failed tests to be equally important. I'm not sure why, except for the fact that I do believe that the successful test sometimes reinforces this illusion that the world can be represented. And I think the unsuccessful test leaves open the notion that, if you're going to make action in the real world, you need to just learn information that you can operate and respond to intelligently. So the search for information, the attempt to learn something, even when it fails, is somehow more independent than the pure simulated result. Like if I plug my sun into the simulator and it tells me the answer, that's less interesting than the active thought process to discover what the sun should do. And the experiment is a way to get your mind to engage with the active process of learning about it. If the simulator tells you something, fine, but what matters is how you're going to use that in the real world. And you can learn something even from these failed experiments. So they wrote the two great books, which still govern a lot of thinking today in the 50s, this book on solar shading, and then the other great one, Design with Climate, which still, bioclimatic design was their idea, that you would design with the local climate. And obviously, this is incredibly salient today. It's coming back, this idea of bioclimatic architecture. Then I think there's also, I don't have as much knowledge of this, but there's a huge the solar movement. There were two already, and we're in the third. There was one in the 50s. There was one in the 70s. And I think we're starting to enter one again, the attempt to use the sun in design. So there were many, many mock-ups, prototype houses that would attempt to use the energy of the sun in the 50s. This one at MIT, the Dover Sun House by Eleanor Raymond and Maria Pelkey's the physicist, and then also these insulating Felix Trombe did all these box experiments, to try to make houses that would radiate in the cold, that would radiate in the radiant spectrum, but not in the visible spectrum, so they would lose heat to outer space, which is something that is actually coming back now. This idea that the radiant spectrum, the separation of the radiant spectrum from the visual spectrum, allows us to lose heat and gain heat separately from whether things are transparent or translucent. And so the notion of radiant heat and radiant cooling, probably people are doing experiments in that today. Dorit Aviv at Penn, one of them. So this sort of back to the physical experiment. This is a current area of research, this radiant heat loss. Okay, then there's the thing that I'm obsessed with, which is wind. So this Mary, I don't know if you guys saw these, and somebody mentioned them to me in studio. These the same person that was doing these sort of time-lapse photos in the late 1800s was also doing wind experiments. So these sorts of photos. Etienne Jules Mary did those photos of the jumping people and the jumping horses, and also did the most beautiful photos of air movement that we have in his study. And many other people, Friedrich Alborn, were doing them in water bath tanks, blowing little particles of dust and moss across the table, and then making drawings of it and building physical models of it. And this became kind of extremely current with the air industry. So wind tunnels became a major part of the world with the Wright brothers. That's how they developed the data for their tests. And also Eiffel had one next to the Eiffel Tower that still exists. And as I mentioned before, NASA built giant ones in the 30s, 40s, and 50s, and even till today. This is the huge one, and they are still used for architecture. This is one of the Twin Towers. They're also used for cars today, still, and they're also used for buildings today, still, because the computational fluid dynamics are not more accurate. Air is too complex. And so there's these giant wind tunnels, and this is meant to simulate the turbulence of the ground conditions around the model. That's what all those little things are. And I have had buildings that we've had to test this way. The city of Boston sometimes requires it, and they send you back something like this, and they say, too windy here, where the red dot is. You need to do something to mitigate your building. Also, the patterns of smoke discharge, often studied in a wind tunnel. As well as high speed flight, because the boundary layer conditions at high speed flight are extremely challenging to simulate, as well as climactic wind tunnels with cars. We did this last year. My students and I, we made one. Tested. This is George's video in that. It's here, by the way. You can use it. People also do water table simulations. This is Guy Nordenson and Catherine Sievert to do coastal resilience. And the other kind of simulation, which I think Jonathan may talk to you about, is the salt bath kind, where you have salt water that sinks and you turn the model upside down and then film it and turn it right side up, and you use that to simulate hot air rising. These are more accurate than the digital simulators. And Salman Craig is the person who's developed this into an art. Okay. Finally, I think the physical models have a huge impact on art. And I think just in their formal language. So these are also from the same time period in the 19th century, the mathematical models, and also sold around around the world in this way. And they were adopted by the surrealists for their strange, unknowable properties and then pasted into photos of other things. This is Man Ray brought them into his paintings in order to sort of dislodge the viewer from understanding of from any particular perceptual framework. So this is Man Ray again. This is Max Ernst collaging the Venus de Milo and the surfaces from these mathematical models together. And I think those models have a huge influence on. Also, I knew these sculptors from this time period, doing inspired by the surrealist work. They were all at the same conference. Barbara Hepworth Naum Gavo and Antoine Pevsner were all at the same conference with Gaudi, where Man Ray brought his photographs of the 19th century cabinet of curiosity physical models. And I think the same destabilization been reinterpreted by Simone Leigh again today. So I think what I'm trying to say is that the experimental models have a long, long legacy, which gets re-understood and owned by various people from various trajectories, and you never know how that experimentation is going to end up. So the physical model is not over. The physical model is a significant part of the world and the openness of the universe, and its capacity to be tested and learned from is still very much alive. And so these are the sorts of things I want from you as a starting point. These are some students last year, little doohickeys that we will see whether they fail or succeed, and you will enter into the same sort of history that I have been just speaking about. Okay. All right. That is the end. I appreciate you coming very much, given how tired and stressed everybody is. And I'm looking forward to seeing all of your work, or not all of it, some of your work today. Okay.
Okay.
Yeah.